Good morning, everybody, and welcome to Using Machine Learning for Whole Loan Data Prep. We'll give it another minute before we get started to make sure a few more people can log in. Prior to that, let's just review a few housekeeping details to ensure this webinar goes smoothly. Just so you know, everyone is muted during the call to help us prevent background noise and to make sure we can all hear clearly. If you have any questions, you will see in the GoToWebinar panel a questions box. Feel free to ask anything in there, and we will get to them throughout the presentation and pause at the end for any additional ones. The last thing is you'll be given a short survey after the conclusion of the webinar. So please fill this out to help us get some feedback on these events. Without further ado, I'm going to hand this over to Elsie Arnell and Matt Steele.
All right, well, hey, thanks. All right, so agenda for the webinar today, we're going to walk through a couple of things before we get to our actual applications. So we're going to start with some of the problems that we face. Individuals who deal with data, these probably will not be new to you, so we'll move through that somewhat quickly. We're going to touch on machine learning just so that we're all kind of on a level playing field as we walk through the actual applications themselves. Then we'll describe exactly what we're doing and, like we said, take some questions at the very end. Problem. Really what we're dealing with is the complexity of data itself. Even when data sets or even attributes are similar, we still programmatically see small differences, even down to header names and things of that nature. So data is messy. Even again, when it's supposed to be the same, it's not. So we see all kinds of small anomalies that end up causing bigger problems later on as data flows through our platform and becomes useful for analysis. So when you're analyzing data or when you're running it through a model, what was a small fluctuation at the beginning or a small difference between data sets can become quite large, and we'll look at that as we get through this. And then just kind of generally, delivery and translation is imperfect and brittle. So we all remember from kind of elementary school when we talk about the concept of encoding and decoding a transmission. They always have a little diagram of two people talking, right? So you think of what you want to say, then you create words. It moves through space and time. It's heard by the ear and it's understood by the brain. Same thing here. Target data source is kind of the source of truth or our where the data lives now. Somehow it gets encoded. It then gets delivered to us. We have to decode it, which is what we're going to talk about here through the webinar. And then we save it in our data store, which we won't cover too much, but we'll probably discuss a little bit as we go through time. So encoding is kind of, we don't want to push the blame on the outside world, but encoding is where things become difficult for us as we're decoding. So you make a change to the encode, and now all of a sudden we have to do something different on the other side. You change a header, we have a problem. You change an order of magnitude or how you're delivering the data or even the structure of your data file, everything can grind to a halt. So these sorts of, that's why the decode part becomes brittle. And so what we're trying to do is build into our ETL systems flexibility and smarts, as it were, that makes it less brittle and more capable of handling those types of fluctuations. One important note here that I did want to cover is that delivery box right in the middle. Seems kind of silly, but we deal with a lot of legacy data systems as well that have been generating data for quite some time. That's positive, but some decisions made in the encode step were based on delivery 10 to 15 to 20 years ago, which is different than delivery now. The internet's a different animal. Hard drives are different sizes. It's a little bit different to store a 1 gigabyte file now than it was 20 years ago. So, but some of these legacy systems still are built around that concept. The older delivery constraints is a good way to put it. And so we're dealing with files that have verbose headers and lots and have delimiters, and flat files with bare bones, no headers, no delimiters, trying to save as much space as possible just because they were built a while ago. So in our world, we're trying to handle all of that as it moves into the data store. So real quickly here, two flavors that we're going to discuss our applications to solve. Field complexity. So here, unpaid balance versus UPB. Mean the same thing, and to a human analyst, that's relatively straightforward, not so straightforward to distill that for a machine itself. Some variables have no meaning, and we have to be able to handle that as well, which we'll touch on when Matt's talking about some of our applications, and headers change through time. So Fannie and Freddie are moving into a world where their flat files actually have headers on them, and they've created these very verbose names in terms of their what they're calling their data fields. Versus in the past, they didn't have headers, which was kind of concern one, and concern two, they had very succinct names, or you could name them whatever you want because you had to add the headers yourself. So as we move through time, people make changes. They make things either smaller and more efficient or more verbose to help analysts understand what's going on, and those changes can cause problems to a more brittle ETL. Okay, numeric complexity. This is really more in the data itself, and our example that we're going to use is a floating point number. So this is current interest rate from 3 different sources. On the right, we have an example of what a client might deliver to RiskSpan here in an Excel file. And you'll see that the interest rates are as hundredths, or literally 4 divided by 100 as 4%. In the middle, we have Ginnie Mae's delivery in flat files. That's the same interest rate or the same field delivered as 43,000. And then on the far left, we have Fannie delivering us a delimited flat file where 3% is 3. So now we have 3 as 3%, 43,000 is 4.3%, and 0.04 as 4%. So the system has to actually be, or our systems need to turn this into something that is similar across all these data sets, so that when we feed these loans into, again, analysis and the models, we get things that make sense. So we don't want the model to think that one loan has an interest rate of 3, another of an interest rate of 40,000, and another of basically 0. We want to tell the model, hey, 3, 4, 5, so that it's so that it makes sense, and the model exactly, so they don't think that it's 0. Okay, so that's the problem statement, basic complexity. Matt is going to start from here and walk through a little bit about machine learning, so that we all have a little bit of a base for what the applications when we get to those.
Thanks, Elsie. So as he just said, I'm going to walk through an overview of machine learning and especially how it pertains to this problem. So machine learning is a really giant and rapidly growing field. You see it all the time in news. I think it reached peak saturation when on Netflix I was getting recommendations for AI-related documentaries and things that were coming out. And it is certainly a focus for us here at RiskSpan. We're looking at lots of different applications, and one of which is the focus of today's presentation on making ETL processes better because they are so important. Every analysis we've done, all sorts of reporting, institutionally, everything is driven by data arriving in the proper format as expected so that everything can run smoothly. So we think this is a great application for some smarts to make things go a little bit smoother. And I'm going to talk briefly about an overview here so we can see how we're applying it at RiskSpan. So very broadly, machine learning can be divided into many different sort of subspaces, but the two that I'm going to call out and make a distinction on are supervised versus unsupervised learning. And the key distinction here is whether or not the data has a target that you are trying to predict. So here I have two dummied up examples. We've got three variables in two data sets, and the data set on the left has a variable that I'm calling target, which means that this is going to be a data set that we can use for some supervised learning. And essentially, we're going to learn from variables 1, 2, and 3, their relationship to target. And once you've defined that relationship mathematically, when you get new data, you can make a prediction on an unseen target. And that's how supervised learning works. Unsupervised learning, which is akin to the data set on the right, there is no associated target variable, but we still want to learn from it. So that can be kind of tricky. So I'd like to highlight something that I put out on a blog, actually, which is an unsupervised learning problem, where essentially we gathered up a couple 100,000 records from some data sets, and we wanted to see if we could map them in such a way that we took tons of variables, over 40, and mapped them down into just 3. And then we wanted to look and try and summarize that data and see if we could notice any patterns. So in this graph here, as I turn it around, you can see we've got 4 different clusters that emerge from the data. And these clusters were not created by some sort of label in the data. This is unlabeled data. All we have is information about the loans. And then what we decided to do was color each loan based on the year that it was originated. So you can see as I'm highlighting over here, this loan was originated in 2013, and the darker ones were originated in the early 2000s. And from this sort of exploratory, unsupervised machine learning approach, we can see that within these clusters, we get sort of subgroups where the different vintages all appear together. So this is the type of analysis that you do with unsupervised learning. You have some data and you want to learn about it. Maybe you have customer information and you'd like to identify customer subgroups. That's sort of the distinction there, is you don't have the overt target in your data set. So now let's talk sort of generally about what machine learning is and isn't. What it is actually is very structured. So without going into any math, there's something called an objective function. And typically you either maximize or minimize this objective function. And you do so with optimization, which is an iterative mathematical process where you figure out how to minimize or maximize that objective. Machine learning isn't magic. It requires this structure. It's also not intelligence in the way that we typically think about it. It's not foolproof in that if you don't structure your objective appropriately and gather appropriate data, you're not going to get great results out of it. And finally, I want to point to something that I've seen out there a lot, which actually comes from the first definition of machine learning, which is the ability to learn without being explicitly programmed. And what the distinction I want to make here is that machine learning isn't writing code in the sense that it's opening a file and writing code to figure out what's going on. What it's doing is it's tweaking parameters in a model to optimize the objective. So I've got this image here on the right, and you don't need to pay attention to any of the technical details, but the takeaway is that we have a model and we have a couple different parameters, each in a different color line, and the machine is exploring those and trying to come up with a way to maximize the score that we want to get, that we stated at the very beginning when we set out for this project. So it's structured and it's optimization, and it requires an understanding of what's going on to make it work well. One example that I think a lot of people have at least heard of for machine learning is linear regression, of which there are many, many flavors. But the reason I bring this up is not that it's the most advanced thing in the world, but it still is that structured optimization problem. So at its core, linear regression is about taking a set of data points and fitting a line to those data points in such a way that the distance between the data and the line is as small as possible. You're going to sum up the distance between the data points and the line, and you're going to keep tweaking that line until that distance is smallest. That's structure, that's an objective, and then there are many different approaches actually of optimizing that problem. Some of which are iterative, but that's sort of what we're getting at. But there are tons and tons of these machine learning algorithms, and they're built for different things. Some of them are better at certain problems than others, but they all follow this pattern of objective and optimization. So the machine learning process, broadly speaking, has a couple different components to it. The first of which is to understand the underlying data that you're going to model. On the right here, I have a heat map taken from an analysis that shows the correlation between pairs of variables. That's really important and has implications for your modeling down the line. Once you understand your data, you're going to generate good data for the model to train and learn from. It's really important that you have good representative data that is similar to what it's going to see when you put it in production. If you train a model on clean data and then you give it very different data in a production environment, you're not going to get good results out of it. Once you have that, you're going to train and, most importantly, validate the performance of the models. Machine learning is often called a black box, and while it can be difficult to understand what's going on under the hood, it's not difficult to come up with a validation process where you get more comfortable with the results that you're seeing, and you become confident when you put it into production that you'll get what you hoped out of it. And then once you've trained it, you implement it and crucially install some monitoring so you can see how your algorithms are performing in real time. You can be automatically notified if something starts to go wrong and you get bad predictions. That's just as important as training a model is monitoring its performance through time. So I wanted to highlight this idea of validation because it is so important. Say you generate your training data. Typically what you want to do is something called cross-validation. This is especially important when you don't have tons and tons of data to work with. The idea behind cross-validation is you can train on part of your data. You can hold out part of it to test against that it has never learned from, and then you can make a prediction on that test set and see how well your model did. And typically that process is repeated multiple times, and as it's repeated, you get a sense for how your model is performing. So now that we've covered some of the overviews here, we did have a question come in that I'd like to take a quick second to answer here on the difference between machine learning and artificial intelligence. So from sort of an academic perspective, artificial intelligence sort of came about with the idea of mimicking human intelligence and creating a really truly intelligent machine that could pass tests like humans do. But in practice, machine learning and AI are very closely related, but artificial intelligence typically deals with a specific type of algorithm called a neural network. There are many different flavors of neural networks that are good at different tasks that are similar to what humans do, such as object detection or putting together sentences and speaking with things like chatbots. Those are all neural networks. They are very advanced, and the reason that they are so good is that they're great at approximating just about any function, whereas most machine learning algorithms are a bit more specific in what they do, although some can accomplish a variety of tasks. So now we're going to talk about how we've implemented this machine learning approach to solve the problem that Elsie talked about at the beginning. So specifically, our goal for implementing machine learning in our ETL processes is to identify information that's uploaded to us automatically. This is a really tough problem because of all the components that make a traditional ETL brittle, but there are a lot of benefits to that, including better user experiences, faster processing time. If we can figure out what's going on, we can kick off things automatically. We can reduce human error. A machine can read an entire CSV faster than a human can open it and start to look at what's going on. And in a way, you can really increase transparency with your ETLs, because in addition to just having an algorithm predict on information, you can have it tell you how confident it was. It can tell you things that it saw and decided to let through. As long as you message out appropriate things about the decisions that are being made, you can learn a lot about what's going on in the process and quickly debug anything that go wrong. So specifically here, this methodology that we're going to employ, we're going to learn from a bunch of data that RiskSpan already has, and we're going to move beyond the hard-coded rules for ETLs that make ETLs so brittle. So rather than having a process break when there's a typo in a header file that we're expecting, we can learn from that, implement these algorithms, and have them say, we know that that's actually okay, and we can continue on with processing rather than having everything stop.
Yeah, and to tie us back to our numeric example, which we are going to follow all the way through here, in a more traditional or what we're calling a brittle setup, you might say that if the interest rate is over 100, just stop. So Ginnie Mae's data would stop, and then we would build a special exception for it and handle it, release that to production, and move on with our lives. But here, we're trying to move away from saying, all right, the acceptable range is X, and get the machine to help us understand what's happening, and then maybe take an action based on that.
Yeah, that's definitely true. So once we've got those rules, we also want to apply the learned information in other ways to make the ETL more robust. Things like quality control get easier when you're learning from your data, and identifying potential bad sources of data or errors that you see is also an outcome of this. And lastly, this idea of continuous improvements. Machine learning algorithms get better with the more data they have access to and the more data they've seen. So we can continuously improve each month as data is dumped on us, and we can just make things more robust through time as we learn more from it. So we've got our approach here, and step one is to learn from the data that we have. So we are going to set up our supervised learning problem here, where our goal is to predict specifically every individual column in an uploaded data set. So the RiskSpan Edge platform has over 4 billion credit records on it. It's got multiple asset classes, which gives us a lot of great data to go and mine to learn from. The great thing about this data is that we've gone through a lot of work to normalize it and learn from it, so we're confident that we know what the headers and columns in these files should be. And since we know the truth record, we can construct our target, which is the actual column identity, and we can build out this solution. And there are 3 separate pieces that are going into the solution that we've designed. The first of which is to take information from headers, and then the second and third are to identify specifically within the data itself columns that are numeric, integers, floats, versus information that is text or strings. So we're going to model around all 3 of these separate pieces of information, and we're going to use that to conduct some supervised learning and hopefully come out with an algorithm that we can put in place to automatically identify columns as they come in. So sort of a diagram here of what's going on. This is a slice of a data set that we might encounter, There are two columns here, state and the current interest rate. The state column has strings in it, which represent the different state abbreviations, and the interest rate has different floating point values in it. And what we're going to do is take just the headers, no other information, pass it into some fuzzy logic, and we're going to generate a prediction of what those two columns are. Then we're going to slice off just the strings that we've identified out of the first column, pass it into a string model, and generate a prediction of what we think that column is. And then we're going to do the same thing with the numeric information, but we're going to pass it to a separate numeric model and generate a prediction. It's important to note that this information is distinct, and the fuzzy logic is acting on the headers without any idea of what's actually in the columns. This is really important because what happens if a file comes in with the exact appropriate headers, but they are on the wrong columns? That could pass right through an ETL process because it says, I was looking for this column and I found it, so let's go process it, when really it could be wrong. But acting independently, we can get sort of independent estimates of what we think the data is. And what we do then is take each of those individual predictions, combine it into a stacked model, which then comes out with our final predictions. So these are acting independently, and each one gives us a probability with what it thinks the column is. That's combined into a stacked model, which will then produce the final output, which we then use to make processing decisions about that column.
And before we go any farther, one thing to point out here is that we go through, there's a lot going on, right, on the screen. But when we get down to that final prediction, we're kind of all the way back to a standard modeling framework where we're looking at just minimizing type 1 and type 2 errors. So Matt mentioned probabilities, and they're very important to us because these models are not intelligent, they're not humans, and it really can't tell you that CURR_UPB is current UPB. But it can tell you that it thinks that there's a 92% chance that it is. And as we move through time, we decide what we're comfortable with, we decide what we're willing to say, yep, that's good enough for us, or that's not good enough, please ask for help. And we draw that line in the sand just like any other logistic regression that you might be doing, where you're looking to balance between type 1 and type 2 error. So lots of complexity, lots going on, stacked model, all kinds of craziness, but at the end of the day, we're still making some type of business decision about how we're going to handle type 1 versus type 2 errors.
Okay, so going into a little bit more detail here on the fuzzy process. We're not going to go into any math, but the goal here, once again, is to use fuzzy logic to identify the column. This is really challenging, especially in a field like finance, where there are tons of abbreviations. There are so many different ways that we've seen loan to value spelled in a file header, yet they all mean the same thing. We also have the problems that Elsie's highlighted before, which is that maybe a file changes over time, maybe someone has a typo 1 month in a header or something like that, and all of those we're hoping to overcome by looking at it with this fuzzy logic. So without going into detail, we're looking for some sort of algorithmic similarity that will tell us, we see this column header and we think they actually mean this. And the way we do that is by leveraging those billions of records that we have and looking at how many different ways things have been spelled before. And if we can map that pretty closely to something that we already know, then we can say, okay, this is representative of this column that we already know about, and we can go on with processing it. So I know everyone's been dying to look at some awesome JSON output from a process. While it's ugly, I hope it illustrates a good point here. This is what we would be getting back from this process. You can see at the top we have an input field that it read out of a file, cur def UPB, and from that we generate 3 predictions that are delivered back based on score. We deliver the column name, but also a definition to help out someone who's reading through a log and trying to figure out what's going on. But then lastly, and most importantly, we have a numeric score that tells us how similar the string in the input field is to the string in the prediction. And as Elsie was saying, that's really important to have that probability, because you can set up a rule where the top prediction, if it has a score of 10, we know not to trust it, rather than blindly saying, give me your top 3 predictions and we'll run with them. Having some sort of a numeric understanding of what's going on is crucial to building out a system like this that actually works. For the numeric information that's taken out of those columns, we're going to generate training data from the numeric columns that we know. Just to pound this in more, there's a supervised problem where the target is the column name. And for our variables that we're going to learn from and learn their associations to the target, we're going to use statistics about the columns. So you can imagine you could learn the difference in mean and standard deviation between a balance field and an LTD field. A machine can do that and 100 other things really quickly, and it can look at a data column and figure out what it is. Once we've done this training, we'd like to apply our model to incoming numeric data, generate predictions, and then really importantly, store that learned information for future use throughout the ETL. The string model methodology is identical, except for rather than generating summary statistics that are numerical, we have to do a bit more work to translate strings into a numeric representation so we know what's going on. There's a process for that. And then we build a model where we learn the association between certain strings and certain fields.
And one thing I think is interesting here is that if we go back a second to the numeric model, when it sees a new interest rate, even if it's kind of off the wall, like say 10 or 12%, that's not really going to change its understanding of what interest rate looks like across 4 billion records. But here in the string model, we really can pick up a lot from seeing new and different data from mostly new and different sources. But think about that state example. If every data source delivered it to us as abbreviation, and then all of a sudden we got names spelled out, using that new understanding of what state might look like and training on that significantly improves our ability to predict state, because now we're looking for VA and for Virginia. And that's where we really start to pick up and can even start to detect the difference between seller and servicer based on how seeing people who are originators but are not servicers in one column, but only seeing servicers in the others. The more sources and basically records that we see, the better we get, and the string model improves more and faster than the numeric model, which again, adding one record of an odd interest rate doesn't change it much, but the first time it sees Guam, our ability to detect state just got better. So it is kind of cool to watch the algorithms get smarter and get more robust as we see more data, and we see that happen more in the strings.
So here's a simple example of how you can sort of understand an association between strings. Here we have just a simple count of observations in the seller name from a particular data set, and you can see some of the more common strings like Bank of America. We can learn not just what strings appear in a certain column, but also sort of the ratio or frequency with which they appear, which also sort of enhances that understanding. So once again, this is sort of our diagram here. We're taking in fuzzy information, generating a prediction, taking in string information, making a prediction, taking in the numeric information, making a prediction, and then combining those for our final understanding in a stacked model.
So looks like nice that you should mention that. Looks like we got a question that is basically just, what is a stacked model? Yeah, great. So we're trying to kind of triangulate a useful word, because there are three models, but generally use more than one model to try to understand what's going on. And there's a couple of frameworks for this. One is called an ensemble, which is where we might just average the outputs of different models and then generate an answer. There, we're doing some simple math around the outputs of our individual fuzzy string numeric. Here, though, we're actually feeding the outputs of the models into another model. And it's kind of important to note that model has never seen raw data. Its raw data is the output of one of the other models. So if you go back to that JSON that Matt showed, that's what it knows about column headers and fuzzy logic. It doesn't know what the columns are or what our sources were or any of that other stuff. All it knows is, I got these three predictions and they had these percent or scores. It's not really good to call them a percent, but they had these scores. One interesting thing there to note is, this is how we start to get over the fact that original LTV and original combined LTV sure do look very similar. And while we can build simple rules like CLTV is almost always the same or bigger, or we can say that, DTI is going to be down in the 40s and LTV is going to be more like the 70s, 80s, 90s, those numbers still kind of look somewhat similar. So allowing the numeric model to make its predictions and say, this looks like LTV, but it could be CLTV. And then allowing the fuzzy field to say, this looks to me like LTV. Then when we merge in the stacked model those two understandings of a high score and a high score, now all of a sudden both the model and us feel good that, yep, that's actually LTV, as opposed to just trying to look at the numbers and getting somewhat confused, or looking at variable names that may not mean much and getting confused there as well. So by allowing these to be synthesized, we get a little, again, a little less brittle, a little more help. And again, it's being fed through a stacked model, which is helpful in balancing between the outputs of those three models without us having to intervene. Okay, so we're going to move on now to kind of a piece of the internals of the ETL. So a lot of what we just talked about is data coming in to the platform and trying to understand it before we begin to process it. Once we get into the actual processing, we're also attempting to use some of these techniques inside of the ETL itself. So as we look at numeric fields specifically, we're going to take some of the information that our onboarding models gleaned from those billions of records, and it's going to begin to help us to understand what to expect as we're processing an individual data set. So now we think we know that this column is current interest rate, and we're ready to go, and we're ready to start processing it. When we bump into the Fannie, Ginnie, client, three different orders of magnitude concern, we want to use some smarts to help us handle that without having to do it by hand or creating a hard and fast rule. So here you can see that we have the mean of current interest rate. So it's basically 6, and that looks a little high for the current market, but remember this is a data set that goes back to 1999. So here we are. That makes some sense. So as we bring in these data fields, we're going to ask the machine to look at and report back what it found. So in the left, which was Fannie Mae, we find a mean of 3. Ginnie Mae, we find a mean of 45,000. And on the far right, we find a mean of 0.04. Now, the machine doesn't have any idea what any of that means until we feed it the expectation. So now we say, hey, this should be 6. And it starts to make decisions based on knowing that this field should probably be around 6. Each of these is going to happen independently, of course, because there's 3 different data sets. But as it operates, it will make some decisions. And then as we write out to our columnar database, you'll see the order of magnitude has moved 3 to 3. 45,000 became 4.5. And 0.04 became 4. And what I'd like to highlight here is that the expectation was not set by RiskSpan or an analyst, right? We ran models and came up with this expectation from data, but it was driven by the underlying data. So 6 is our expectation, not because we think the interest rate should be 6, but because that's what we found and that's what we've learned. Then it's important to note that I didn't tell the order of magnitude what to do. It looked at 45,000, decided that did not look like 6, and made the decision that it needed to make to change 45,000 to be 4.5. That is a relatively simplistic use of machine learning, but nonetheless, the machine learned from data and then made a decision without our input based on what it had seen in the past and what it was being presented with in terms of the data in the column. So maybe not as overly exciting as building a vocabulary and training to understand a string column based on past experience, but nonetheless really important to us because, again, if we feed our models an interest rate of basically 0, we're going to get all kinds of crazy outputs. But if we can normalize the data to be 3, 4, and 4, we're going to have many fewer headaches across the platform. So I think all right, so we got a few more questions. One question we got is, what kind of files can be used as an input? Great. So for the process as it stands right now, we need, this is that kind of structured learning idea where we took an input and went to a target. And at the moment, we do need some version of a delimiter. So we're not, the fixed width format, we do have to pre-process before we can handle it. On top of that, we are currently using or requesting headers so that the 3 models all get something to work with. The fuzzy model is important to how we understand data as it comes in. So flat file, basically, headers and delimiters. But beyond that, no special requirements for delimiters or order of the file or anything like that. Just needs to be a structurally sound delimited file. Okay, and then question number 2 that we got is, what kind of infrastructure can be used? So for the most part, the models themselves, they get trained and then applied later. So they don't interact with the 4 billion records at any given time, but they do have to touch them at some point. So when you're doing that, it's nice to have some robust infrastructure, and we are 100% on the cloud. our company happens to use, well, actually, we use different cloud providers, but we're using cloud servers, and we interact with the data once, and then we become a little bit lighter weight in terms of you could apply this to a relatively small data set on a traditional machine, your laptop as an example, but for the most part, it's all living in the cloud. Cool.
Okay. So we're going to take a break from questions for now. I'm going to go through this final section of our presentation here, and then hopefully we'll open up for some more at the end. The next section is about our graph database technology that we're using to help out this process even more. So this isn't specifically machine learning. However, it is a new technology that's seen a tremendous amount of growth recently, and we think there's a lot of potential for it to be used well within this domain. So I want to briefly start with an overview of graph database technology. It's pretty straightforward, but it is a newer concept. So rather than having a traditional relational database where you have data in sort of a table format like an Excel spreadsheet, you have nodes and relationships. And relationships are also called edges, if you ever hear that terminology. Both nodes and relationships can hold data in the form of key value pairs, but they are tremendously flexible. So nodes and relationships can have labels on them and also have the data stored within them, but the fundamentals are that nodes have relationships to other nodes. So here's a very simple sort of schema where you have a gray data set node, a relationship labeled as contains, and then a blue node representing a column. And going into a little bit more detail, at the bottom of the second picture, you can see, if you highlight that column node, you can see information that we've stored about it, like the name, the format, and its type. So we have this ETL process, and we have all this data, and we wanted to make it easier for analysis. So we decided to take the meta information that you would normally find in data dictionaries and leverage graph database technology to make it more useful. And I'm going to switch over to our database to show you what's going on. So in this first image here, I'm going to zoom out quick so it's a little bit more clear of what's going on. This is an overview of the data universe. And even at such a high level where you can't read any of the labels on the nodes, it's actually visually intuitive as to what's going on. So the gray nodes are data sets. The blue nodes are columns that are contained in those data sets, and that's signified by the yellow relationship lines between them. So in the upper right corner, you can see there's a data set that has tons of unique columns to it, and it doesn't have many connections to the other data sets. If you move clockwise, you see there are two data sets that contain a lot of nodes in common, also with little interaction with the other data sets that are in this visualization. And then lastly, on the entire left side, you can see there are a lot of intermingled data sets, and their relationships have sort of pooled all of the columns that are in common to the center of that image. And those are all nodes that are very highly, they're ubiquitous throughout these data sets. So this is useful from a high level to see what's going on, but to show you an example of how this can help with analysis, imagine if you wanted to quickly figure out what data you could combine across data sets. Well, you can query this graph and return back only the columns that are in common. So here we have three separate data sets from Fannie Mae, and all of the columns that are in the center here are found in each of them. And once you have this information, you can use it, but you can also inspect the relationships to pull out more specific information. So for example, here we have the field property occupancy. And if I pull it over here, I can highlight this relationship from this data set. And if I do this drop down here, it's a little bit difficult to see at the bottom of the screen, but we've got all this information stored in the relationship. So we do a lot of normalization. This shows you values that are mapped from their original value to a new enumeration. We also have the source definition from whoever provides this data set. We have the location of it in the flat file and the name in the flat file. Lots of things that we can leverage right into our ETLs. And if I highlight the relationship coming from another data set, you'll see the list of map values has changed. This has unique date ranges and descriptions, but the point is you can store tons of information specific to the data set while retaining that intuition that both these data sets contain this column. So it's really helpful for answering these types of questions quickly, as opposed to browsing a PDF of a data dictionary that was dumped out by a more traditional database. And lastly, just one more simple example here of a query. If you wanted to do some research on balances throughout these data sets, this is a query that just said, bring me back anything with UPB. And here we have sort of a spattering of nodes for all the different UPB fields that are found in the database. You can just as easily bring back the data sets that they're contained in. But the point is you can readily access this type of meta information in a way that's useful and makes your analysis easier and faster. So that's sort of the highlights of this graph database technology. As I mentioned earlier, it's becoming really popular because you can do some really cool things with graph algorithms that you can't do with traditional databases. But we found that it's a tremendous use case is for this sort of meta information about your data and your data dictionaries. So now we have a couple more questions. We're going to leave up our contact information, but if you have any questions, feel free to type them, but we'll go through some of the ones that we have now.
All right, cool. So one of them here is, what is the target variable in the order of magnitude model? And I apologize if I misspoke. The order of magnitude is really, I guess, probably more appropriate to refer to it as an algorithm. It is taking in some of the learned information from the smart ETL's models, but it is just attempting to optimize its way from the data that it's seeing to its expectation. So it is attempting to manipulate each of the interest rates that it's seeing when it's operating against current interest rate, and get itself to the expectation or close to the expectation, or as close to the expectation as it can get. So my apologies if I misspoke, but I wouldn't really refer to it as a model as much as just an optimization algorithm.
Okay.
But it is learning, so I guess that's why we were trying to include it in the presentation today, because yeah, it learns through time, gets better through time, and is making those kind of optimization decisions by itself.
So the next question is about the graph database and whether or not you can do data lineage with it. And my answer is that yes, you definitely can. So I highlighted some of the flexibility, but it's important to note that with these relationships, you can have multiple relationships out of the same node. You can have recursive relationships back to itself. So you could easily sort of enhance this structure that you're seeing here to include a direction from a data set into a column, and then take that column and give it a relationship that points to the next place that it lands. And in that relationship, you could store all sorts of information specific to how it's going on. And you could further sort of enhance this by adding in information about data ownership and curators, by adding in information specific to who is responsible for this data set, or generating this, or maintaining it. The flexibility of being able to store all sorts of labels and key value relationships in this database means that it's incredibly flexible. And you could definitely do some data lineage with this.
Okay. So I think, assuming there are no more questions coming in, it doesn't look like anyone's asked any after that. We're going to wrap this up, but thank you guys so much. If you have anything, feel free to email them at lc@lernl@rispend.com and Matt at msteele@rispend.com. Thank you guys so much for taking time in your day to watch this, and we hope you enjoyed it. Thank you.
Thank you.
Thanks.